Welcome back. In this video, we'll consider yet another example for the expansion of this function in order to find the Laurent series of the function. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now, the biggest method or the reason why we are doing this, recall that in our last video, we already took an example that showcased how the Laurent series was evaluated. However, what makes this very, very important to talk about is to talk about the process, what happens when you have a degree at the numerator equal or greater than the degree at the denominator. In this case, before you embark on the partial fraction process, it is needed for you to first and foremost bring out or extract out the quotient such that it will then be on the remainder, which would be a partial fraction, or which would be a proper fraction to which you then find the partial fraction of. What do we mean? Now, of course, the very first thing we know is for this function, let's say let f of z be equal to z squared minus 3 divided by z minus 1, z minus 2. Now, if we expand the denominator, just so that we are clearly sure of what exactly is going on, the denominator would become z squared minus 3z plus 2. Now, from here, we can immediately see that we have ourselves the degree at the numerator being 2 and the degree at the denominator being 2. They are both quadratic equations. So before we proceed to look for the partial fraction, the very first thing we'll do is to take the long division. By taking the long division, we would be able to extract out the quotient. Now, of course, going through the motions of the long division itself might not be totally necessary if you are able to truly discern what the quotient would be. And that would be done by simply taking the division of the longest at the highest degree divided by the highest degree. So z squared divided by z squared gives you 1, that is the quotient, and then you multiply by the divisor, and at the end of that we subtract. So from here we see that what we would have left is 3z minus 5. This, of course, would be our remainder, while 1 would be our quotient. So that way we can see that f of z would be split based off these two parameters. Now let's put that all together. This means that f of z would be equal to 1 plus 3z minus 5 divided by z squared minus 3z plus 2. Now on this proper fraction here, which is of course the remainder divided by the divisor, we can then proceed to utilize the partial fraction. Now we would extract that 3z minus 5 divided by z squared minus 3z plus 2. Of course, if we return the denominator to its factored form, we have 3z minus 5 divided by z minus 1, z minus 2. So this means that this, of course, opens to a divided by z minus 1 plus b divided by z minus 2. Now, of course, we can cross multiply or we can take the LCM, whichever one you prefer. But we would have a multiplied by z minus 2 plus b multiplied by z minus 1, and this would be equal to 3z minus 5. Now, by cover up, which of course, as I said in the last video, is fastest when you are dealing with distinct factors. If you set z minus 2 to be equal to 0, this would mean that z equal to 2 is a value that we can use, such that we would now have a into 0 plus b equals 1. And from here we can see that b is equal to 1. Similarly, if we set z minus 1 to be 0, we would have that z equal to 1 can be used in the equation. And from there we would have minus a plus b into 0 would of course equal minus 2. So from here we see that a is equal to 2. So we now have a representation that suits both ways and of course allows us to solve with this partial fraction. So f of z now can be written in full as 1 plus a over z minus 1, that will be 2 divided by z minus 1, plus b, which is 1 over z minus 2. Now, we've done the partial fraction. The next bit of business is to deal with, of course, the poles. Now, the poles in this case, you set the denominator to 0, z minus 1, z minus 2 equals 0. This would imply that the poles are z equal to 1, and of course z equal to 2. Now, from here, if we proceed to create the region of validity, right, from 0, of course, to infinity, let's place 1 here, and then let's place 2 here. We see that we now have 3 possible splits, from 0 to 1, from 1 to 2, and then from 2 downwards. So it means that the possible regions would contain 0 less absolute value of z less than 1, 1 less than absolute value of z less than 2, and then 2 less than absolute value of z less than infinity. These are the 3 possible regions of validity. As always, as I said, if the question provides you a permissible region, then you will then check which of these regions fall within the permissible region before you evaluate. Now, we have these 3 regions. You can take a bit of time to consider the first region and see how the Laurent series in the first region looks like. Then return back to this video to look at the solution with us. Now, for the first region, we would have that absolute value of z less than 1, of course, immediately follows the absolute value of z is less than 2. So it means that for positivity to occur in the denominator, 1 minus z must be greater than 0, and then 2 minus z must be greater than 0. That's the positivity region. So it means that f of z here would switch from this guy to minus 2 divided by 1 minus z, then minus 1 divided by 2 minus z. Because remember, as always, the goal is to always have a positive denominator. And then from here, we would have 1 minus 2 divided by 1 minus z. This has no issues. But here we have minus 1 over 2, 1 minus 1 minus z over 2. So that we can have the denominator starting with a 1 term. So there we go. Now from here, we can simply write out the sum to infinity of this geometric series. We have that f of z would then be equal to 1 minus 2 summation, of course, k starting from 0 to infinity, 0 to the power of k. That is what we would have in the first term. And then we'll proceed to the other one, minus 1 over 2 summation, k starting from 0 to infinity, z divided by 2 raised to the power of k. This is what we have. So now we have these 2 sequences or series. You notice that both of them are both analytic parts. And in fact, this one is still part of the analytic part as well, which of course can be combined together into the full set of solutions. So we see exactly what we have. So we can do the summand and bring all those summands together, because of course they are all analytic parts, and then we can sum them all together. Remember, when k equals to 0, you have a constant. When k equals to 0, you have a constant here as well. And then you're going to have 1 minus 2 minus 1 over 2 coming out. And then you can bring those constants outside and then start the counter from 1. Or you could return this back into the summand and have yourself a collated result. I would like to see how best you'd want to rewrite this in the comments. So please let me know. Now we have done our first region, which is 0 less than absolute value of z less than 1. Let's now proceed to the second region and see how exactly we can solve for that. Now, we will first and foremost start off by stating what the second region is. 1 less than absolute value of z less than 2. This would simply imply that absolute value of z is greater than 1, and we have that absolute value of z is less than 2. So it means for positivity, we must have absolute value of z minus 1 greater than 0, and then 2 minus absolute value of z greater than 0. Now remember that f of z originally is 1 plus 2 divided by z minus 1 plus 1 divided by z minus 2. This is what we have originally. Now, if this is our function originally, then if we apply this bounds, it means this remains as 2 divided by z minus 1. And then this would change because 2 has to be higher, or 2 is greater than the absolute value of z. So you're going to have minus 1 divided by 2 minus z in this case. Now, from here, how do we proceed? Again, we realize that we have to make the first or the leading term in the denominator 1. So we have plus 2 over z into 1 divided by 1 minus 1 over z. And then here, we would also have minus 1 over 2 into 1 divided by 1 minus z. We have these two terms present. Now, if we do this, the next thing or the next bit of business we can look at is, okay, based off this representation, now I have attempted to complete the Laurent series for this region as such that you could go through the motions yourself and see if you can get to this final line I have. Now, I've written 3 lines. Of course, we have used the same sum to infinity of the geometric series that we have always used. So work your way and see if you can also get here with us. Of course, if you decide to proceed beyond this, also do let me know in the comments. And if you need more clarity as regards to how we have always been turning this fraction into this series, and you probably want us to discuss more on the geometric series and the representation of the sum to infinity of the geometric series, you can also let me know in the comments. Now, more importantly, this is just still our second region. We now would have to talk about our third region, which goes to infinity. Now, you would notice that in the first region we took, we had just analytic part present. Now, in the second region, we now have a mixture of the analytic part and the principal part. Now, in the third region, what will we have in front of us? I will proceed to infer that we would have only the or would have majority of the principal parts functioning and probably one being the only member of the analytic part. Is that true? Take a minute and try to solve this on your own and see if that is correct before you join us for the solution. Now let's go. From here, we are simply saying the absolute value of z is greater than 2, which obviously means immediately the absolute value of z is greater than 1. So it means absolute value of z minus 2 makes it positive, and absolute value of z minus 1 is positive. So if we set that into the function, f of z will be equal to 1 plus 2 divided by z minus 1 plus 1 divided by z minus 2. We would have no reason to change this representation based off the region we're dealing with. So from here, all we'll just do is to simply factorize out so that we have a leading 1. And that is exactly what we will do. So we have 1 divided by 1 minus 2 over z in both cases. Now from here, we can then write out the Laurent series. So f of z will now be equal to 1 plus 2 over z summation k starting from 0 to infinity 1 over z is the power of k plus 1 over z summation k starting from 0 to infinity 2 over z raised to the power of k. Now, if you figured out how we shifted notation here, then it would not be so much of a problem to do the same thing on this part. Now, you notice, as I said earlier, that this is the principal part, this is also the principal part, and the only analytic part present is just 1. So this also tells us something very, very interesting, that the 3 regions give us 3 different kinds of Laurent series for us to work with. So from here, what exactly would we have? We could rewrite this and say summation k starts from 0 to infinity 2 divided by z is to the power of k plus 1, then plus summation k starts from 0 to infinity 2 raised to the power of k divided by z raised to the power of k plus 1. That's what we're going to have. And then from here, we could decide to, of course, shift the notation. So we have 1 plus summation k starting from 1 to infinity 2 divided by z raised to the power k, then plus summation k starting from 1 to infinity 2 raised to the power of k minus 1 divided by z raised to the power of k. We can have this as well. So based off these notations, we could of course factorize these two. I would advise you to factorize. I am much interested in what the results of your factorization would be. So let me know in the comments. But what we have done is we have fully solved and found the the Laurent series expansion of this function, and their region of validities, giving the Laurent series for each of those regions. You would notice that this is a very rigorous process, but it is also very straightforward to understand. I'm sure you've been able to pick one or two as regards to how to solve questions that need you to find the Laurent series. Now, we would be moving on to the next phase within this complex analysis playlist that we have started quite a while ago. But before we do so, I would leave you with a question for your practice. What we have done in the last 2 or 3 videos would definitely be sufficient enough for you to do so. And you can always rewatch the videos so you have clarity of it. Once you've solved them, please do let me know in the comments what your solutions are. And if you need more clarity, you can also let me know in the comments and I would make a video on it per request. So this is our question. So we have to express z squared plus 1 minus iz plus 2 divided by z minus iz plus 2 as a series, as a Laurent series. So, of course, check the degrees. Do you need to do long division? If so, do it. Next, find out the poles. Next, or do your partial fraction. Then find out the poles. Then find out the regions. How exactly would the regions change if you have a complex number in this case? Would it be so much an effect, especially when you're looking for the radius? Yes, no, maybe. Figure it out. Let us know in the comments what you end up getting. Then find the regions and also find the Laurent series for each region, right? I am looking forward to what your answers would be and what your attempts would look like. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.